I could not change the date. Well, if I put it on Wednesday, I did it by accident, but I'm certainly willing to like have them on different days. I meant to do it all on Thursday. I didn't realize there'd be anybody in both classes. So. But if it's written on the calendar as Wednesday and people have made their plans around it, then it will be Wednesday. All right. Yeah, I'm not going to change anything that's on there. All right, so homework questions. Yo. 39. Which one is that one? I'll pull it up. If I can pull it up. 1 second. 39 on 2.3. 2.3. 39. Find an equation for the plane tangent to the graph of z equals e to the x plus y cosine xy at the point 0, 1 e. Is that right? Okay. 39, 2.3. So the function we're dealing with is f of x and y is equal to e to the x plus y cosine of, where is that? Cosine of xy at 1, 0 e. 0, 1 e. Okay, and I'm finding a tangent plane, right? So delving into my library of things that I've learned in this class, I know that the equation of any tangent plane, should it exist, must be of the form h of xy is equal to f of ab plus fx at ab, x minus a, plus fy at AB, y minus b. Man, this is terrible. Okay. Now, I actually know what f of AB, a and b are 0 and 1, and f of AB is e. Right? I can read that off right away. So a is 0, b is 1, and f of AB is. Now, at least I can reduce the problem with this. H of x and y is equal to e plus f x at 0, 1 times x minus 0 plus fy at 0, 1 times y minus 1. So making progress. We got one more thing we got to do, which is we got to find these partial derivatives, right? To evaluate the sort of slopes in the partial derivative directions. So if f is equal to e to the x plus y cosine of xy, then by the power of product rule, fx should be equal to e to the x plus y times the x derivative of x plus y, which is 1 times the cosine of xy plus e to the x plus y. The derivative of cosine is minus the sine of xy times the derivative, the x derivative of the inside function, which is y. And if you evaluate that at 0, 1, 0, 1, you get e to the 1 times 1 times the cosine of 0 plus e to the 1 times minus the sine of 0 times 1, which is e. You tell me if I'm wrong, by the way. That's what I compute, e. All right? Okay. Now let's do fy. Probably the same because it looks like a symmetric function. So I bet fy of xy is going to be equal to e to the x plus y. The y derivative of that is also 1 times the cosine of xy plus e to the x plus y untouched. The derivative of cosine is minus the sine of xy, and then the y derivative of the inside is x. So it's even more 0. So fy at 0, 1 is going to turn out to be e to the first times the cosine of 0 plus e to the first times the sine of 0 times 0, which is e. And so I think this equation is the, I feel a lot of e's running around this equation. So you get e plus e times x plus e times y minus 1. That's a whole lot of e. But that's the equation of tangent. So basic form. All right. I promise I've even like problems on exams to do It'll be like this. Okay. Zeros and ones, and so things turn out nicely. Anything else? Yep.
40, please.
40, which was
Same question.
equation for the planes tangent to that curve that are parallel to that plane. Okay. 40. Okay, so what is the function this time? 40 from the same section is x squared minus 6x plus y squared. All right. X squared, oh, y cubed, okay. Okay. So that's our function. We want tangent planes that are parallel to 4x minus 12y plus z, 4x minus, too many things in my head, 12y plus 7z, 7z?
Z equals
Plus z equals 7. Oh, man. Reading like this, like 6-point font on my screen too. So, okay. So the idea here is really when I say parallel to this plane, I mean, how do I detect if planes are parallel? The same normal vector, right? They say normal, the planes are parallel. So what I'm going to do is I'm going to do the terribly intensive process of figuring out what the normal vector of this plane is. And I'm going to find places where the normal vector to the tangent plane up here is parallel to this vector, right? Which means there's a multiple of that vector. So let's call this, we'll call this n. Okay, so the question is, what is the normal vector to that tangent plane? Like, how do I, if I got this function, which is some surface, how do I find its normal vector? Yep. Yeah, so the easiest way to do this is to say, this is just a fact about our construction of how to find tangent planes, was that the normal to a tangent plane, I'm going to point out that the way that we did this was we took the vector 1, 0, fx, so this is sort of the slope in the x direction, and we crossed it with the slope in the y direction. Yep.
The 4x minus 12y plus z. That plane is perpendicular to the z function, right? First one.
Perpendicular to the z function?
Sorry, normal. Yeah.
This normal is not perpendicular to it's perpendicular to the surface. So you think about this surface up here is kind of going like this in space, right? And there's places where on that surface, there's a tangent plane that sits onto it, where the tangent plane that you get is parallel to this vector, or perpendicular to this vector, right?
Perpendicular.
Yeah. So there's some surface floating around. We're saying, here's this plane up here.
And which one is that?
This is this guy.
Okay.
And it has some normal vector n, which is equal to 4 minus 12, 1. And down here, I want you to imagine this is a three-dimensional figure down here, right? Somewhere down here, we're looking for points down here where if I drew the tangent plane, you would get the same normal vector. The location might be different, but the tilt of the plane is the same. This is like, say, this is in calculus 1, this question is always asked as, find the points on the function who have slope 2. The same question is saying that, like, oh, figure out where on the curve x squared plus 7x, the tangent line has slope 2, right? This is exactly the same question, but like in sort of 3 dimensions. Okay, and then the normal to a tangent plane was given by the cross of these two vectors, because this is the x slope and the y slope, and that turned out to be minus fx minus fy 1. So this is the normal vector to the tangent plane. So let's write it down. Now the beautiful thing about this is that means I don't have to worry about finding multiples, because the number here is a 1 and the number here is also a 1. So I literally just are going to have to figure out places where fx is equal to 4 and also fy spits out a negative 12. So what is fx for this function? 2x minus 6. What is fy? Remember, these are all relative to this surface, right? here I'm thinking fxy is equal to z, which is equal to x squared minus 6x plus y to the third. So fx is 2x plus 6, fy is 3y squared. And so now what we're looking for is places where these vectors point in the same direction, all x and y, so that 2x minus 6 comma 3y squared comma 1 is parallel to 4 minus 12, 1. What's that? Oh, yeah. Minus, yeah. That's 60. Okay, now, normally when you have parallel vectors, you got to be careful because parallel vectors would still be parallel if they were pointing in different lengths, right? But here, I don't need to worry. I just have a 1 here and a 1 here, so I can just do a direct comparison.
That crossing results in the
Yes. Yeah. This cross results in this vector. This is like saying the partial with respect to x and the partial with respect to y vectors. And when you cross them, you get the normal to the tangent plane there. So what we're saying is the tangent plane is built out of one vector in the direction of x and one vector in the direction of y. Yep.
Is it enough to show that, do we have to show that the actual numbers inside are equal, or do we need to show that they could be scalar multiples of each other?
I mean, in this case, the only way that they're not, I mean, because they have a matching component, we don't need to worry about the scalar part, right? Because since they have the same components, this is fixed, it can't move, so I don't need to worry about the scalar multiple part. There's not, that won't exist. Now, I mean, if it was possible, if we'd taken the negative of this, I'd have to account for the fact there was a -1 here and a 1 here. Okay, so what are the values that make this work? Minus 2x minus 6 is equal to 4, minus 3y squared is equal to minus 12. So x had better be equal to minus 1. And there's a couple of y values though, right? Y is equal to plus or minus 2. So as long as all of that stuff holds simultaneously, we're going to get the same normal vector out, which means that there's two places where that happens. The point 1, 2 and the point 1, minus 2. So these are points on that. These are the xy coordinates of the points on the surface where that tangent plane hits. But if we were, this is just the x and y values. If you want to say what the XYZ place is, right? What's the point on the surface where these tangent planes are parallel? You actually have to evaluate the function on these 2 points to finish the problem to get the x, y, and z's. Yep.
So at these 2 locations, including the z, the tangent plane have the same direction.
Yeah. So like basically what we're saying is it's a situation like this or something, right? Where there's one point right here where we have the tangent plane and another point over here where we have the tangent plane. And those are precisely the places where we have the same normal vector, right? That the planes are oriented in the same way. So like that can't happen on a sphere, right? On a sphere, there's one unique tangent plane for each direction, right? The surface, this is sort of like it's a lumpy surface in some way. If there's 2 places where the tangents have the same direction. Yep.
Could you explain that seven, like the 1, 0, 0, 1?
Which one?
Like
This?
you get to there. Yeah.
I mean, the idea here is that these vectors come from the fact that if you have some surface and you have a point that you're computing on and you need 2 vectors to build a tangent plane, what you do is you say, okay, go this way and look at this vector that's in the x direction. For every 1 unit of change in the x direction and no units in the y direction, do that much slope. This is telling you the slope as you move in 1 unit of the x direction. That's what slope means, right? Slope means 1 unit in x, what's the y change? But it's a z change this time. For every 1 unit in the y variable change, this is what the slope should be in the y direction. So it's saying, as you go this way, grow like this. And as you go this way, grow like that, right? And then, because those are both vectors contained in the tangent plane, you say, oh, well, if it's a plane, if that's going to exist, I can get the normals. If I've got 2 vectors inside of it, I get the normals by crossing them. All right. Yep. Nope. Yep. So what you're doing there is then you're talking about if you had flipped this around the other direction, like suppose that you use the version of this where this vector was fx, fy minus 1 instead, like you cross the other direction, right?
No, I meant like if the normal vector was like 4, 12, 1, so it's negative.
Oh, I mean, in that case, you have to make this match, right? Because like the idea here is that these things are going to be scalar multiples of each other. It's vectors are parallel also if they are scalar multiples, right? But this vector is fixed. And so essentially you need to figure out ways that,
Right. I'm just saying, like, if you had to solve for that equation where it's negative 3y squared is equal to 12, for instance.
then it would be impossible. No, sorry, I didn't understand the question. Yeah. If you're going to get a complex number out the other side, then there is no place where it happens.
What's the equation?
What? Well, if you know the xy, then you can just go back and use the h of xy equal to f of ab plus fx ab x minus a plus fy of ab. And you just take that and recompute it.
So we're not plugging it back into it.
Well, you need to plug it in here to get the z value, right? You need to know this fab in order to have this plane happening. Right, you need all those bits. Okay. All right, we good? For now, anyway. Cool. Okay, so let's talk about more derivatives today. Right, so more derivatives. Today we're talking about section 2.4, which is called higher derivatives. Okay. So of course, in one variable calculus, I can take one variable calculus, at least if it makes sense, I could compute the second derivative of a function, right? I could at least try to compute this. I mean, why not? D by dx of d by dx of f of x, that's something we regularly try to compute in calculus, right? I think it makes sense. Actually, anybody remind me what this measures? So, okay, physicist in the room. Okay, so acceleration. What else? Just in terms of the graph itself, the second derivative measured concavity, or when the second derivative is equal to 0, we're at something called inflection point. If you took 241, you should have also learned the second derivative is associated with like how fast a curve is turning, which is a quantity called curvature. Don't worry if you don't remember that, we are going to see it again. Okay, so if you didn't take 241 or it was a million years ago and you don't remember, or your teacher just decided not to do it because it was the end of the quarter, I promise we will talk about it again. Okay, if you want to get ahead on that one, you could look at something called the Frenet frame, which is one of the sort of core ideas of pulling apart motion in 3 dimensions, right? That's one of the things that this is used for. Okay, so second derivatives are used to measure acceleration and things related to acceleration, like how fast something is turning. So one variable, a useful quantity, just derivative of derivative, and we denote that by second derivative. Now, of course, in several variables, we have an issue, which is that there's lots of choices to make, right? So the idea in several variables is that as we repeatedly apply derivatives, we have to keep track of what order we do it in, what we're taking derivatives with respect to. So I'm just going to define the second partial derivatives of f of, let's just say x and y to start with. We'll build this up. We'll start with f of x and y. And really, the only thing to deal with here with the second partial derivatives in the first computation is just keeping track of what the notation is telling you to do. So the second order partials with respect to x. So second order partial, usually we use like WRT to be with respect to x. Just mean take the partial derivative with respect to x of the partial derivative with respect to x of x, f of x and y. Do it twice. Of course, that's an awkward notation. So usually we'll say, so there's this notation, squared partial dx squared of f of x and y. Of course, that's an awkward notation. So the laziest possible way to write this, which is probably the best, is fxx. And you read it left to right. This is going to be important when we start talking about mixed partials. This says take a derivative with respect to x and then take another derivative with respect to x. So for example, if you had f of x and y, how do I make myself not insane doing this? X e to the x squared y. Sure, why not? And I took its second partial derivative. Well, I can't take the second partial without taking the first partial. E to the x squared times 2xy. And then I've made myself a product rule, I guess. So the second derivative with respect to x is just the derivative of the derivative, like in one variable. So if I take another derivative of this with respect to x, now I have to use the product rule. So I get an e to the x squared. Yeah, I'm happy. Times 2xy times the 2xy that was already there, plus e to the x squared y times the x derivative of 2xy, which is 2y. So there you go. Second derivative with respect to x. These almost always, like for any remotely complicated function, you get product rules falling out the other side. Because you're going to be chain ruling out these pieces. So, okay, likewise, d by dy of d by dy of f of x and y is equal to d2 dy squared of f of x and y, which is f y. And we're not done with the derivatives because we have two other ways we can take second derivatives. This said do x and then another x. This says do y and then another y derivative, but there's two more. Those of you that have taken combinatorics can imagine that the second derivative is out of control. If there's like 9 variables, there's a whole lot of second derivatives running around, right? Okay, which is an argument for the notation that we're going to introduce later. So the next are the mixed partials. So these are often called pure partials because they're just double in one variable. The mixed partials are where we use both variables. So d dx of d dy of f of x and y is a mixed partial. Which one comes first? The y or the x? Oh, who said x? So the way that mathematicians think about this, and physicists, is whatever's closest to the function is what gets first access to it, right? So that says hit it with the dy first. Then after you hit it with the dy, then do the x derivative. So this says do the dy derivative first and then do the x derivative. Okay. Or, okay, what order am I going to put this in? Yx or xy? Yeah. Left to right. This is, many people get confused here. Okay. All right. And then the other one, which is this one. I'm going to give you guys a chance to impress me in a second here. Okay, so those are the mixed partials. Now, one of the most important theorems in all of vector math and in all of sort of the calculus of two variables says that there's a relationship that exists between these two things a lot of times. First off, what is the relationship? They are the same. Do you know what the conditions are for when they're the same? Does anybody in the classroom know what the name of the theorem is that says the mixed partials are equal? That's not the Cauchy-Euler equations. That's what says that a function is analytic in complex analysis. Yeah. Clairaut's theorem. Oh man, you guys are good. All right. So normally we don't actually care about these things being different because normally they're the same. So one of the things that shows up a lot in applications in engineering and physics and mathematics is you make this assertion. So a common assumption in practice. To the point where sometimes it goes unstated is, you basically say, suppose f has, in fact, I'm going to write this up here. It's so important. And then we'll state Clairaut's theorem. Okay, so here's the condition. F from a domain X in R2 into R is called a C2 function. This is the single most common assumption in all of modeling mathematics, is that F is C2. A function is called a C2 function if all first and second partials. Any guesses? I heard somebody whisper it. What behavior do the first and second derivatives have to call function C2? Continuous, not just exist. You gotta say more than exist. I showed you an example last time of like on the board up here of a function where the partials existed, but the function went haywire. It's not enough the partials exist or the second partials exist. They must be continuous. So a function is called C2 if all of the first and second partial derivatives exist and are continuous everywhere. Which is not as much of a stretch as it seems, because it means that you want functions that basically act like polynomials or rational functions away from asymptotes, right? Now, why is this such a common assumption? First, it makes all the solutions to second order differential equations nice. Like, if you're going to be solving a second order differential equation, it's nice to know that solutions are continuous, right? Second, you get Plural Theorem. It says if f is C2, fxy is equal to fyx. That's the R2 version of it. Now we can check that real quick if we don't believe it. Maybe just with a quick example here. So suppose you have f of x and y is equal to, I don't know, what's something that's not going to be, but x squared cosine of x y to the third. We're going to compute the two mixed partials and we'll check they're equal, which is really me checking to see if I can do partial derivatives. I suspect this is going to have continuous second derivatives, right? Because those are pretty nice functions. So fx is 2x times the sine of xy to the third times y to the third. I don't think I forgot the minus sign that goes out front. Take the derivative of cosine. Yep. Oh, okay, did I make a mistake?
You did.
I did. It's a product rule. What am I doing? Yeah. Let's just pretend that's not on video. 2x cosine of xy cubed, even professionals, minus x squared sine of xy to the third, y to the third. Thanks for catching that. I don't want to take fxy is equal to, okay, well, the 2x gets left off. 2x sine of x y to the third times 3y squared x. Is that right? No, because I chain ruled something that
What if we don't start with the product?
oh, you know what? This is what am I doing this to myself? F of xy is equal to x squared y plus y to the third x. There. Now I've got a nice polynomial to do. Oh, days. 2xy plus, now double check me and make sure I get that right. Is that right? Yes. Okay, cool. I can do derivative. What if I take that and I take its y derivative? What do I get? 2x plus 3y squared. Yep. Hopefully, you guys trust me? We'll see. If I violate Clairaut's theorem, then you'll know I've made a mistake, right? Okay. Is everything continuous so far? Sweet. Okay, let's keep going. Fy, on the other hand, is equal to x squared plus 3y squared x. this function again, but with the y derivative. And so f yx, if I take the x derivative here, I get 2x plus 3y squared. Okay, sweet, math works. Okay, so this and this are equal, and it's no accident. We like to work with these functions because it's computationally efficient to do so. I'll point out if I've made a mistake here, at least I made it symmetrically. Because the thing about Clairaut's theorem is it's actually quite a bit more powerful than the way you learn it when you learn it for the first time when you say mixed partials are equal. It actually holds for CK functions for the kth partial derivatives all the way down, right? So what I mean is really what Clairaut's theorem, so there's this sort of like, you know, like a leveled up Clairaut theorem. Says if f on a domain X in Rn into R is CK, so that means the kth partial derivatives to all orders exist and are continuous. Then any partial derivative consisting of the same derivatives can be performed in any order. Then any mixed partial can be computed in any order.
So is this kind of like reading the idea that if something's conservative, then you can go like, for example, like forward and then right?
It's all basically built out.
Okay.
Yeah, I mean, what we're going to see eventually with Clairaut's theorem. I mean, Clairaut's theorem basically says you don't ever need to check any directions except if you're in a C2 vector field. You know, you need more, but yeah, if you get the second derivative as being continuous, it means that you never have to look at any directions other than the coordinate directions. Yep.
So when you say CK.
When I say, I should say the kth order. I gotta be careful. The kth order mixed partials. Like the second partials are in a C2 function, the second mixed partials are all equal, but the first derivatives weren't, right? Here, what we're saying is, suppose like as an example, if you had f being a C3 function, so 3 continuous partial derivatives, all third order continuous partial derivatives exist, right? Then I could say something like d to the 4 dz dw dx dw of f, say of x, y, z, and w. If I had a 4 variable function and I computed 4 derivatives, that would be the same as any other order I put those same derivatives in, right? I could put the w's first if I want. d dw, d dw, d dz, d dx. It wouldn't matter what order I did it.
So why not include anyway?
It doesn't have to be. I mean, I'm not forced to take a y derivative just because y exists as a variable. But what I'm trying to point out here is, as soon as you got a pile of symbols, you can shuffle them around in any order you feel like. Computationally, this is efficient because usually you can get rid of a lot of structure of a lot of these functions by being very particular about the way you compute the derivative. Like, for example, if you had some giant pile of symbols and one of them was a d by dy, but the function had no y's in it, you probably want to do that one first. I mean, I like taking 0 to 9. Yep.
I'm a little confused on that. You're not just changing the order, right?
Am I using a different combination?
Twice.
dw twice, a dx, and a dz.
Oh, I thought one of those was.
No. I meant to be really specific. It's the same set of symbols can be shuffled in any order. If you have different symbols, those aren't equal, right? Clairaut's theorem in 2 variables is easy because there's only 2 symbols. You can do x, y, or y, x, right? There's no other choices. But even in 3 variables, you have stuff like, what you need is f of xz is equal to f of zx, and f of xy is equal to f of yx, and f of yz is equal to f of zy, right? All of those must be equal to each other. So they're mixed, but they're mixed with the same symbol. Yep.
Wait, is this one actually a C4?
Yep.
Okay.
Yeah. So this is a C. For, yeah, I meant to write 3 derivatives. Yeah, for this must say a CK function will have its 4th level mixed partials all equal to each other. Of course, a C4 function is also a C3 function, because if you're 3 times continuously differentiable, if you're 4 times continuously differentiable, certainly you're 3 times continuously differentiable. So if your C4 and your 4th order partials mixed are all the same, well, you're also C3. And so your 3rd order mixed partials will also all be the same. So that's an enormous, I mean, again, assuming this kind of regularity makes computational efficiency like super high level of computational efficiency. Very often in practice, you don't actually need a C4 function. What do we call a function that can be continuously differentiated forever? In fact, I know one. E of x, that's a really good one. F of z is equal to e to the z. Now we're not going to restrain ourselves to the real numbers here. We're going to write it in complex numbers. So that could be differentiated forever. And every derivative is e to the z, since e is continuous, all derivatives are. Anybody know the name of that? I'll tell you what the symbol is. C infinity. So a C infinity function is a function that can be infinitely differentiated and the derivatives are continuous. So every polynomial is C infinity. I mean, eventually it turns into 0, but 0 is perfectly differentiable. So any guesses as to the sort of function this is okay for? You guys have seen these before. In fact, you saw them extensively when you took Math 143. They were under a different name. Yep.
Power theory.
Anything with a absolutely convergent power series turns out to be infinitely differentiable, because if you have a power series representation, you can just keep taking derivatives, right? You're just a giant polynomial. So those functions are called analytic. So functions that are sort of representable with power series tend to be, I mean, those are the functions that are infinitely differentiable. Right? If you see any complex analysis, if we say holomorphic, that's another word that means infinitely differentiable. Smooth is another one. What's that? It is, yeah. They're actually not equivalent, but it is necessary. The other name for this that you might see is smooth. So why smooth? Well, derivative measures rate of change, right? So what we're saying is the rate of 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 change, no matter how far down you go, varies smoothly. So those functions have no corners in a really, really strong sense. There go the nicest function. Somebody got a hand up. Okay. Okay, so we did Plural Theorem. All right. Okay. Sweet. We got enough time to talk about at least a new idea here. So we've done enough. Okay, so have we done enough? Let me just ask, have I done enough computations of partial derivative? Okay. So if people run into trouble in their computations of partial derivatives, let me know so I can give more examples of what to work through. Okay. I just don't want to, it's really easy to, it's hard to find a balance between teaching you guys new stuff and also larding the class down with a bunch of me computing away at the board. What is the chain rule? What is the chain rule? Just for calculus 1. What's that for? Of what? Not quite. Composed functions. You're talking about the product rule, which is you've got f times g. But if you have g living inside f, right? G plugged into f, and you do compute the derivative, use the chain rule. What does the chain rule say? I mean, you guys have probably done 100,000 chain rule problems in your life at this point. But do you actually remember what a statement of the chain rule, other than just it's a process where I have to take the derivative of the inside function? What does it say? I mean, there's meaning in the chain rule, right? So what does it say? There's all kinds of conditions on when you're allowed to do it. But when you're in calculus 1, everyone ignores conditions and just follows those algorithms. Right? What does it say? I'll give you, go ahead. F of g of x is equal to F prime of g of x. Oh, okay, so the derivative of f of g of x is
F of G of F, like with G still in there. Times the derivative of G. Yeah, that's what I said.
all right. Hold on. Wait. It's the derivative of f, but with g still in it.
Yeah.
Which derivative of f is it then? You say, see, we weasel this all the time in calculus class and just write f prime, right? Here's what you're doing. You're telling me it's f prime of g. I guess that's what you're saying. Times what? G prime of x. That sounded, doesn't that look kind of iffy? Like we got symbols running all over the place. I mean, you're not wrong. You're not. This is the chain rule. I mean, the way most people encode it is, oh no, there's this g here. You just leave the inside function alone. You just do the derivative of the outside function, leave the inside function alone, take the derivative of the inside. But there's actually a formal way to state what this is doing. In fact, there's a massive assumption we've made about the way f and g interact with each other, where for this to even make sense at all. Which is what? I mean, what are all the possible conditions that we think that you, I mean, what should we say here? What do we need to know about f and g in order for this theorem to make any sense? Because remember, we're trying to lift this up to lots of variables. Yep. Okay, so it had better be the case that whatever set g lives on. So we're going to define here, we're actually going to change the notation so that it matches up with the way the book does it, right? So what the book says is, okay, we're going to consider a function. I guess we don't have to do that. Yeah, so let's say g lives on some set t. T is contained, I don't know, we're in one variable calculus still. T has some domain in R, and it spits out some range, right? It had better be the case that the range of g lives inside the domain of f. Because if g is spitting out values f doesn't know what to do with, the whole thing breaks down. Right? There's nothing to be done, right? This comes up in practice so much more often than it does in a calculus book, right? Where you have this composed function, but this is spitting out values that f doesn't know what to do with. And then you get an overflow error in your modeling software or something. But I don't know. I can't evaluate that. So whatever g is doing, it better spit out something in the domain of f. F, on the other hand, is going to take a domain x in R into R. Then we say, if I took the derivative d by, okay, now what variable am I taking with respect to? Like, what is the independent variable here of this whole problem? What's the independent variable? Well, little x, right? Can I change it so that we're doing little t so that t can live inside t? Would that be okay? I'm gonna say here, I want g to be a function of t, and t lives inside of t. Okay. And then f can be a function of g. That's really what we're doing here, right? F is a function of g, where g lives inside x. We have an original domain t. We map it over into some new set called x, or called the range of g, but that had better be inside of the domain of the function f. And then f takes that and it maps it over into the range of f. Make sense? This is what's going on in the composition, right? So when we're taking a derivative here, there's more going on than like f of u times u, f prime u times u prime, which is how I learned it. Okay, so there's these domain conditions we have to worry about. Is g spitting out values f knows what to do with? So what we're really doing when we do this, if we put all the derivative symbols in, is we're saying that d by dt of f composed with g of the independent variable t is equal to d by dg of f of g times d by dt of g. There's actually two different derivatives happening here. There's a g derivative, and then there's a t derivative happening, right? And they're different. We hide this all the time with the prime notation. But what's really going on here is we're thinking of f as a function not of whatever's on the inside, but of a variable g. It's just that the variable g is reacting to its rule because g is also a function. Okay. So this is the object that we're going to try to generalize here. And the way that we keep track of what's happening is with what's called a variable hierarchy. So what is the independent variable of this function? The independent variable is t. This is the independent variable. And it gets fed into g, which we think of as something called the intermediate variable. That gets fed into f, which is the dependent variable. Right, so there's two relationships happening here. How do we compute the chain rule? Well, if you think about our formula for the chain rule, the change that change in t imposes on g, we think of as dg dt. And then there's this df dg. And the total change is the product of those two things, right? The total change of a function is like the change that the intermediate variable has with the change in t times the change that the dependent variable has in terms of its intermediate variable g. So the chain rule can be read off just by starting here at the independent variable and reading across until you get to the dependent one. So the total derivative df composed with g of t is equal to df dg times dg, right that way, d by dg of f of g times d by dt of g of t. The reason we need to do this sort of level is because we're going to introduce functions with lots of variables and lots of intermediate variables. And we need a way of keeping track of what's happening when we have lots of things going on. So anybody have any guesses or memories, maybe even memories of what I would do if I had a function where the intermediate variable was a function of other variables? Let's suppose now that I have a function f of x, but x is a function of s and t. Let's suppose everything's differentiable and all the domains line up. What is d by ds of f of x? So I have an s and a t. Those are my independent variables, right? And they both feed into a variable x. And x is what's modifying f. Is that like a correct variable hierarchy here? There's a one intermediate variable x. It's being fed by s and t. And ultimately, the dependent variable is wiggling around in this function f, right? F has one input, x has two inputs. What do you think df composed with x of s, d by ds of f composed with x is? It's not a trick question. You can just read it off. What's the pathway I use to get from s to f?
Yeah.
So there's going to be, so this path, this is the df dx path, and here we get. So the pathway from s to f goes df ds, I'm sorry, not df ds, dx ds. We're going to talk more about this next time, don't worry. dx ds, df dx. And so we're going to build expressions for chain rules that are going to have webs of inputs and webs of intermediate variables. And the pathways that we use to get from one independent variable to the dependent variable, every pathway will have its own contribution to the total derivative. So chain rule in the multivariable setting turns into this massive matrix of derivatives that we can keep track of. And that's where we're kind of headed with this. Right? So with derivatives and compositions, things are more complicated. I will say that the reason you care about this is because change of variables is a composition of functions. So every time in your guys' class you've ever used polar coordinates, you've actually done this without realizing. X is equal to r cosine theta and y is equal to y sine theta.
Those are equations where you're replacing one set of variables with another set. All right.
Sorry.